Hello guys. I welcome you all to day 4 lecture, Neural Network Structure. So this is our day 4 in the deep learning series. So we will be looking at neural network structure. So the basic roadmap of today's course, today's lecture is basically it will be a small lecture and you will feel like most of the things have been already told to you. So we'll be looking at neural network structure, layers in neural network structures, hidden layers, weights, and biases. And then we will be looking at what is forward propagation. Indirectly, all these things have been told to you, importance of forward propagation. And then we will be looking at parameter calculations in a neural network structure. So this is our basic roadmap of today's lecture. So I think we should first revise what we have done in our last lecture. We have done the perceptron model and activation functions. We have looked what is perceptron. We have also looked basically the learning rule of perceptron, and then we have done a code example on AND gates, and we have seen that how at first weights and biases are assigned, and then they learn with every iteration or epoch, the weights and biases are changed. If there is a misclassification, then the weights and biases are updated. And then we know the basic perceptron learning rule, and then we have seen the difference between single layer perceptron versus multi-layer perceptron. Then we have also seen the activation functions. We have seen three types of activation functions: the sigmoid activation function, the hue activation function, and tanh activation function. So we have also seen the ranges. Basically, we made the uh, graph of them. And then we have also seen the different frameworks like TensorFlow, PyTorch, Keras. And then we completed our day 3 lecture. So now we'll be doing our day 4 lecture. So our day 4 lecture is based on neural network structure. This basically you have studied the neural network structures are computational models inspired by human brain, consisting of interconnected layers of nodes or neurons. You know, neurons are basically the uh, basic unit which mimics the biological neurons in our brain. If you remember that cat brain thing, how the scientists basically tried to build an analogy between the neurons and the biological neurons. So they are designed to recognize patterns, classify data, and perform various tasks in machine learning and artificial intelligence. Key components of neural network neurons. The basic units of neural network analogous to biological neurons that receive inputs, process them, and produce output. This you have already seen. This you already know. Since my last lecture or second last lecture, we have done hands-on calculation also. In last lecture, I think we have done layers. Yeah, in AND gate, we have done how things go, how we calculate the weighted sum. So just we will go reading our notes. So layers. Neurons are organized into layers, which can be characterized as input layer, hidden layer, and then output layer. This, input layer receives, it is the first layer that receives input data, and then we have hidden layer that process data. It is an intermediate layer, and then output layer is present that produces the output of the network. So this is a neuron's output is computed. So you know that first weighted sum plus bias is calculated by it is written right here. This is basically the formula. First we calculate weighted sum, then add bias, and then we pass it to activation function to get the output. This output of a neuron is passed to another neurons. So this is basically this is the flow is maintained. And then you know that already know that xi represent inputs, wi for weights, b for bias, and then then the z is the output of them, basically the weighted sum plus bias, and then we pass it to the activation function to get the output. So layers in neural networks, input layer, yeah, again the same thing which you have already studied the definition. The input layer is the first layer of neural network that receives the input features. So this is basically the same thing. Function, it converts the input data. There are many types of functions like loss function, optimization function, activation function you have already seen. loss function and optimization function we will be studying in our, I think, day 6 or day 7 lecture. So basically, there are functions integrated with we already have seen that activation function integrated with the neuron, and it converts the input data into format that can be processed by subsequent layers. So we also have a normalization function. We will be looking at the different kinds of function, how they basically work and how they are attached to our models. And we know the structure. Each neuron is the input layer represents a feature of the input data. So basically here, if we draw, so if we consider, yes, uh, if we have basically this thing, and then we have kind of four hidden layers, and then suppose an output layer. So basically, if this is our input layer, so this three input layers basically represents a feature of the input data. Like if we prepare, if we are doing, suppose, take an example of a house cost basically. So price of a house, price of a house. So if we are considering the input, basically we are doing a regression problem. So we have to predict the price of a house based on the input features, like what we can consider the basically the area coverage of the land, area of the land on which the house is built, area of land, and then uh, we can also consider the built-in area, which is in built-in area we can say basically say like how many bedrooms or how many basically yeah, basically we can attach it with how many bedrooms. Either it is 2 BHK or 3 BHK or 4 BHK. So number of bedrooms, if we say, 1 second, number of bedrooms. And the another input feature can be like in price of a house. Then we can see the locality. If we consider some localities to be very good, some localities the cost of the house basically differs with the locality. So locality can be an input feature. So these basically these three we will be passing in our input layer, these three things, and then we'll be predicting, considering a regression problem, we will get the predicted price of the house, predicted price of the house. So basically, these three input features we will be passing, and then there will be internal calculation, and then we will get the basically first our model will be trained, and then the output will be produced after during the inference time. First, in training time, the weights will be assigned, and our model will be trained, and then we will be doing inference. During the inference, we will pass basically the input data only will be not passing the ground truth or the output data, because that will be only passed during the training time. We will be looking basically how the model is trained, and then basically this and during inference time we'll be passing the vector basically of area of land, number of bedrooms, and the locality. Maybe locality we can consider like 5-star locality or 4-star locality, 3-star locality, 2-star locality, or 1-star locality. So 5-star locality, that means we are giving a number 5 to that locality, which means that locality is very luxurious, very posh locality. And for 1-star, like it may be some locality very poor. So basically, we will be passing area of land in square meters in square feet, or number of bedrooms. We will be numbering number of bedrooms. Like if 3 BHK, then we are giving three. four or five accordingly, and the locality it's either five or it's either three or it's either two, and then we will be training the model. The during training, basically provide a label or ground truth or the output of that, and then when our model is being trained, then we'll be doing inference. In during the inference time, only these three input features will be passed, and the model will predict basically. So basically, the each neuron in the input layer represents a feature of the input data. So each every neuron here is representing the feature of the input data. Like first neuron is representing the area of land, and the second neuron number of bedrooms, and third the locality. And then there will be, as you know, every neuron will be this thing. You basically know that every neuron will be attached to every other neurons of the next layer, and then the whole calculation will be performed, and the weights and biases will be assigned. So this is basically what each neuron in the input layer represents the feature of the input data means. So the number of neurons in the input layer corresponds to the number of features of the input. That basically this is the same thing which is written. Here is also an example for a data set with three features: height, weight, and age. The input layer will be have three neurons. So the input data provided to us is divided into height, weight, and age, and then these three will be passed to the model. So we can consider the input layer here. The input layer will be of three neurons because we have three category of input data. Basically, we have three features. To hidden layers, basically we have completed input layers. So what are hidden layers? Hidden layers are basically the intermediate layers. It is between the input layer and output layer. This is already known to you. So if you go to the definition, the hidden layers are the intermediate layers. Basically, they lie between the input layer and the output layer. Intermediate layer that perform computation and transformations on the input data. Yes. So what are the functions of hidden layer? They extract high-level features from the input data through the applications of weights, biases, and activation functions. So what are high-level features? This I think I have told you, but let's revise it once. So if I draw, so consider consider this as an input layer, then we have an output layer, one more hidden layer. No, so basically, sorry, pardon me. This is our input layer. Then we have intermediate layer, and then we have an output layer. So consider this as a output layer, and this to be input layer. And consider this all the three as hidden layers or intermediate layers. So consider this first hidden layer, second hidden layer, and third hidden layer. So the first hidden layer is we can say is extracting low level features. Complete the spelling basically, and then second layer is middle layer features, and the third layer is extracting high level features. So what are basically low level features, middle layer features, and high level features? High level features are basically, we can say that they are more complex and abstract features. Like if we take case of NLP task, natural language processing task, then A low level features will be a character, basically a token. Like it can be a single character like A, or it may be a single character like B or C. And middle layer features are more like more if we add more basically if we add more words to it, like it may be a word like more character to it. Like earlier in low level features we are having a single character as A, or a single character like full stop, a single character like comma, or any type of single character. Then if we add it a more greater or more level to it, then it will be like a word. Like middle layer features can be a word like a dog or a cat. Or so basically, it is now we have reached more abstractness or complexness. So as we go through different layers, we will get more complex or abstract thing. So in high level features, it can be kind of a sentence or a basically sentiment sentence. In like if we are doing a CNN task, then low level features can be basically it may be a little edges or maybe corners or edges of that the input image we have passed, and then middle layer features will capture more things. Like it may start capturing a shape, it may be capturing like shape like square or any kind of random shapes. And then in high level features, the whole image may be extracted. Like the feature may be extracting, if we are extracting an eye or any dog or cat or anything, basically more features or complex image will be captured. Like the faces may be captured of a dog or a cat of a baby. So in low level features like in CNN tasks, only edges, corners or lines are captured. And then in middle layer features, the shape starts to be captured. And then in high level features, the complete images starts to be captured, like faces may be captured, like in nose structure, eye structure, everything will be started to capture it. So hidden layer features are basically which are more complex or abstract. So I have told you in how NLP tasks, low level features are like tokens, which are basically translated to like characters. This will be studying the different types of tokenization scheme in NLP, but the basic gist is like in low level features, like characters are captured, and then middle layer feature like a word starts to be captured, and then in high level features, the whole sentence starts to capture. More abstract complexness basically grows. In CNN tasks, I told you that in low level features, basically edges or shapes or points or lines are captured, and then middle layer features, the shape starts to be captured. And then in high level features, the complete face or any complete images basically starts to capture. So in hidden layers, they extract high level features from the input data through the applications of weights and biases. So they take data, input data, then they start capturing low level features, then middle layer features, and then high level features. So basically, they starts to capture everything. A neural network can have multiple. This, I think, the function I have already told that how the different features, different kinds of features are extracted. And yeah, basically, if I remember in the first day one lecture or day two lecture, I've already told how the features are, how early layers work, and then middle layer works, and then the later layer works. So, structure you already know. A neural network can have multiple hidden layers, allowing it to learn complex patterns. The number of neurons in hidden layers is a hyperparameter and can be adjusted based on the problem. A neural network can have multiple hidden layers. You already know there can be like many layers in it. Like if we are making a custom model, then we can add different number of layers from some 2 to 3 hidden layers to like thousands of hidden layers, allowing it to learn the complex pattern. As the layers grew, then the chances of learning complex pattern grows until unless we face the problem of vanishing gradient descent. But basically, increasing the number of patterns, the number of layers basically helps. But I would say that it is a hyperparameter because we need to tune it according to our needs, according to data. If like data set is very big, then we can prefer a
model, basically we can prefer many hidden layers, but if we have a small data set, then we should go through less hidden layers, because again the problem of vanishing gradient may occur. But if we have large amount of data, then we need more layers to incur the or extract the features from different images. We have a large volume of data set, so basically we can incur more features or more knowledge from our data set and assign weights accordingly to the different number of hidden layers. So basically, the number of hidden layers it is written here is a hyperparameter and can be adjusted based on the problem. So we have to tune it according to our problems, according to our volume of data, and according to different which perfects. We have to basically optimize. We have also we have pre-trained models like in CNN. If I say they are a pre-trained models like ResNet 101, we have ResNet 50, then we have ResNet 18. Like in ResNet, we have 100 hidden layers, and then we have 101 because it translates to 100 hidden layers, and then we have one fully connected layer. And similarly goes for ResNet 50. These are basically the pre-trained models like VGG16. Also in ResNet 50, we have 49 hidden layers, and then one translates for the fully connected layers. So basically, we have we that number of hidden layers is a hyperparameter, and we have to tune it accordingly. We will try to see it in codes, and we will be studying the documentation also. I will be attaching the pages of a documentation page which you should, or the article pages which you should study on your own. And we will be trying to cover this, how to tune the hyperparameter for better understanding. And then we have output layer. We have output layer. The output layer is the final layer of a neural network that produces the network's output. Yeah. It summarizes the information processed by the hidden layers and make the final prediction. I already basically this is the output layer, and it will basically give the final results or output of the model which we have basically trained. According to the input features, it will produce the output. And then we structure the number of neurons in the output layer depends on the type of problem. This is very important. Basically, for binary classification, we have one neuron with sigmoid activation, and for multi-class classification, the number of classes, they are basically more classes. In binary classification, we have only two classes. So we have to divide our data accordingly to in two classes, and then for multi-class classification, the number of classes increases. Like if we are passing, if we are training a model, and then we have if we are passing an image and we have trained a model accordingly, like it will classify dog, cat, cow, horse. So basically, it is a multiple class, multi-class classification. If we are classifying like a model is trained to classify dog and cat, then we have binary classification. If a model is trained to classify between dog, cat, cow, and horse, then maybe more classes like donkey. Then we have a five class classification problem. So this we'll call a multi-class classification. For regression, we have one neuron with linear activation. For regression basically we can say we get a number, and in classification we get the classes, and we directly don't get the classes, we get the probability of that class. This I will try to look in the website too. For this I would like to show a website. I will look at that website and tell you in the later part of the lecture. And example, for binary classification, the output layer will have one neuron. So this thing I will be telling you through a website. I remember the website. So, weights and biases. We'll be looking the earlier part. Now we go to weights and bias. Weights, you already know. Weights are the parameters which get trained. First, we assign random values to the weights and biases, and then with every epoch, if the misclassification is there, then the basically losses are there, and so with the loss, the our model basically learns the different kinds of weights. So weights are the parameters that adjust the input signals to the neurons, controlling their influence on the output. So if you remember the last lectures and example, then we have seen at that we have seen how weights are randomly assigned, and then uh, how basically if there is a misclassification, then the weights get updated with iteration. If we run basically epochs or an iterate and we get weights updated if there is a misclassification of any type. So earlier the weights are randomly assigned and then they get updated. So weights are parameters which gets updated according to our the input data and the function. Each connection between neuron has an associated weight. This you already know. Like in weights calculation, I have told that every input feature has a weight assigned, and every neuron has a weight assigned to it. So if I go to this part, like this has a weight, this neuron has a weight here assigned, then weight here, and then here. So W1, W2, W3, W4, and then again this neuron will be weights assigned like W, if we say W21, W22, W23, W24. So this will be this neuron will also have weight assigned with basically there will be a weight assigned to it. So if we each connection between neurons, so if we see this connection with this neuron, this connection with this neuron, this connection with this neuron, and this neuron has a weight assigned to it. So if better if we write it, this also basically so this is W1, W2, W3, W4. So basically, every connection of a neuron will have a weight assigned. We already have studied that every input feature have a weight assigned to it, but every input feature with a neuron has a weight assigned to it. So, like this input feature with this neuron has a weight assigned to it. This input feature with this has a weight assigned to it. This input feature with this neuron has a weight assigned to it. And this input feature with this neuron has a weight assigned to it. So basically, and every neuron attached with a neuron has a weight assigned to. If we attach this neuron to this, then there will be a weight assigned this to this, weight assigned this to this, a weight is assigned, and this to this, a weight is assigned. So basic thing written in this is that weights are basically a parameter, and then there is a every neuron attached to a neuron has a weight assigned to it, and every neuron has also a bias attached to it.
Biases. So biases are additional parameters added to the weighted sum of inputs before passing through the activation function. This you already know. Before passing to activation function, we get weighted sum and we add bias. So what is the function of bias? They allow the activation function to be shifted, enabling the model to fit the data better. In day one lecture only, I've taught you basically if we have a straight line passing from the origin, if we make this. So if we add a bias term to the equation, if we suppose this straight line is y is equal to mx, where m is the slope, and this is the x-axis, and this y is the so the vertical axis is y, and if we add a bias term to it, we get the equation like this. So y is equal to mx plus c. Basically, we get the equation like this. So this graph belongs to this equation. So this is the c term. This is the bias term which is added to the equation, which brings a shift in the equation. You can see that the line got shifted by c. It shifted from the horizontal axis and it is shifted parallelly by C. It is shifted in vertical direction by C. So this is the C is some value. It may be shifted downwards also. Like if C is a positive term, and if we write an equation like y is equal to mx minus c. So if c is a positive term, so that you can see that the line is shifted downwards. So basically, the bias terms brings a shift. They allow the activation function to be shifted. So basically, the bias term brings a shift, which which also brings a shift in the activation function. Like if the activation function is a step function where we if the value greater than zero is considered one, and value equals to zero and smaller than zero is equal to considered as zero. So if we add a bias term like two is added to zero, so it brings a shift in the activation function, because now if two is added to zero, then it is greater than zero, so the value will be one. Like our step function, if we are considering the same step function like which you already considered, where if value greater than 0 is considered to be 1 and value smaller than equals to 0 is considered 0. So if we are considering this step function, so basically if we add a bias term in our this equation, so if this a bias term, suppose 2 is added or 1 is added, and if this equation is 0, so if 2 is added, the equation, the answer solution becomes 2. So if now the same values passed to the activation function, the output will be 1. In previous case, the output would have been 0, but now if 2 is added, the bias term is added, the value turns out to be 1. So this brings a shift. The bias brings in a shift, enabling the model to fit the data better. So basically, this enables the model to fit the data better. Initialization biases are also initialized randomly, and it is usually a small constant term. So basically, it initialized to zero or a small constant term. You have already seen in that previous example where we have taken the value from the code we have already run, and then we verified that value. So moving forward to the forward propagation. So this forward propagation you have already seen many times. You just don't know the correct word. What we have been doing is the same as forward propagation. Forward propagation is the process of passing input data through the neural network to obtain predictions. The function of forward propagation is it involves the calculating the weighted sum of inputs. This you have done, you have now done many times, that we are basically calculating the weighted sum of inputs and then adding bias and then applying activation functions at each layer. So at each layer, at each neuron point, we apply activation function. This you already know, and basically this thing you have been doing many times. The same thing is repeated. The term which is given to the thing we have been doing is called forward propagation. So the steps of forward propagation is that the input layer, we receive the input data, this you already know, and in then hidden layer the weighted sum plus is calculated and bias is added to it, and we are then applying the activation function. So basically, this is called forward propagation because we are forwarding our input data into different layers of neurons in hidden layers, and then another hidden layer, and then we are applying an activation function at each neuron point, at each equation we get, and then we finally send the outputs of the hidden layers to the output layer where the final output we get. So the output of the hidden layer becomes the input to the next layer. So this is the same thing written. So in output layer, we if you look at this equation, Z output, W output, this you already know. If we write it, Z output is equal to weight of uh, output into A hidden. A hidden is basically the input of B. So A hidden is basically the output of the hidden layer, which is taken as input to the output layer. So this equation is A hidden it is basically the output of the hidden layer. So when after applying the activation function, the output which we get acts as the input to the output layer. So A hidden is basically the output of hidden layer, which acts as the input to the output layer. So the same is thing written. This is the activation from the hidden layer. So this is the output, the activated output from the hidden layer, the output of neurons from the previous layer. The same thing which I told you is written here. The W output, the weight matrix connecting the hidden layer to the output layer. So all the neurons of the hidden layers, the previous layer is connected to the output layer. So basically, it is the weight matrix. Actually we do matrix calculation. So that also I will show how the matrix calculation. Once we complete this lecture, I will try to show you how the matrix calculation is done, how the we multiply the weights. So B output is the bias term added in the output neuron. So we added B output. B output is also written here, and Z output is the raw output before applying an activation function. So this is the raw output, and this raw output of output layer will be passed into an activation function. With after passing from the activation function, we get the final output. So apply the activation function Z output. So we get basically the final output. Example of forward propagation, yeah, this actually I prepared the how the parameters calculation, and if we look at the examples of forward propagation, then if we are assuming a simple neural network, so we have two neurons in input layer, and then hidden layers also we have two neurons, and then the output layer we have one neuron. Importance of forward propagation. So as I told you, forward propagation is the same thing which we have been doing. So in forward propagation, basically the importance are like in prediction phase, forward propagation is crucial for making predictions based on input data. And basically this is the same repeated things which we have done in training. The results obtained from through the forward propagation are compared with true labels to calculate the loss, which is essential for back propagation during the training phase. So here the word back propagation is very important. So if you remember the last time I told you how the learning rule of basically learning rule works, we if you remember the formula, we know the formula, basically how the weights and biases are updated. So weights and biases are updated using the back propagation method. This is how the weights and biases are updated. Uh, uh, so basically, we will be covering this back propagation and forward propagation specifically in some like in day 6 or day 7 lecture. But here it is just how the weights. If you have been ever asked how the weights and biases are updated in a model, then you will be saying that we use the backpropagation method to update weights and biases. So uh, so this is basically a small gist, and if you look at the model evaluation, so it allows evaluating the performance of the model by comparing the predicted outputs with the actual outputs. So basically, when if you have covered the data science course, you must be knowing that if we have not given a validation data, so we divide our training data. Like suppose we have a training data of around we have 100 data points if we consider 100. If we say we have why it's not working, 1 second. So if you say we have 100 data points, and then we divide this 100 data points into 80 data points for training and 20 data points for validation. So why validation is helpful? So if 100 training points are given, then we have the training data with the basically with the ground truth or label of that data. So 80 training data helps the model to learn. So this amount of data helps our model to learn, and this amount of data helps our model to validate whether we are doing things right or wrong. Basically, our model is trained correctly or not. How what is the amount of validation accuracy, or if we have made our validation losses very small. So basically this validation helps us to learn basically that is it our model overfitting, or is it underfitting. Overfitting and underfitting words you must not be knowing, I think, but this will be also be telling. We will be making a graph between training accuracy and validation accuracy, and we will be also be making graph of training losses and validation losses. So basically, we do validation check to know that actually it happens when model learns in every epoch. Sometimes it happens that model even learns how basically that it works. It doesn't get a pattern. It just try to mug up what the training data is and try to overfit it. But if we provide a validation data is basically the data which is not seen by our model during training phase. It's like just we are checking how our validation data is working. So this we will be this also will be doing this thing will be covering using code. We have a lot many things to learn from code basically. So this thing also will be learning from what happens. This thing will be learning from code. It will be very helpful if we learn this thing from code. It helps us to understand more properly. So this is basically the importance of forward propagation, and then we will be this is very important, calculating the numbers of parameters in a neural network. So in a neural network, the number of trainable parameters determined by the weights and biases in each layer. So number of trainable parameters. My writing is trainable para- yes. So number of trainable parameters is a sum of weights plus biases. So we'll be calculating the number of trainable parameters. We'll be looking how the number of trainable parameters are calculated. So for a layer with an input neurons and output neurons. So if we take the example of yeah, we are considering an example. So we have three input neurons, and then we have hidden layers, four neurons in hidden layers, and two in output layers. So if we connect this, 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 and you know how we basically how we connect this, this, this. If I try to make in different colors, then it will be more helpful for you to understand. So if I connect this, oh shit, yes. Similarly, we do this. And rest, you know, basically what we are doing here. This is already told to you. And another color which this. So basically, every neuron is connected to the other neuron, and basically the neuron which are connected, there is a weight between these two neurons. So this there will be weight distribution like W1, W2, W3. You know basically how the whole pattern is working. So if we calculate the number of weights in between these hidden layer and input layer, then we by logic we will multiply 3 into 4, because for every neuron connected to another neuron, there is a weight associated. So it will be 3 into 4. For this neuron, there will be 4 weights for this neuron, because this neuron is connected to other four neurons. So there will be 4 weights for this neuron connected to these 4 neurons, and then for this also there will be 4 weights, and similarly for this also there will be 4 weights. So will be 3 into 4. So 12 weights are basically in between these input layer and this hidden layer. And you also know that there is basically 4 neurons for this. So this is input layer. Input. This is not exactly the neuron thing. Basically, particularly input thing does not have bias. These will be having bias terms. So if we add 12 plus 4, then we will get 16. And then again we will calculate for this. We have two. For this particular neuron, we have two weights associated because there are two points. Because this neuron is connected to two neurons, so there will be two weights. And for this also, will be having two weights for this again. So there will be 4 into 2. So we get 8. And then there will also be a bias term added. So 8 plus 2, we will get 10. So uh, 10. So if we sum all this thing, then we get this is 16 actually. So this is 16. Yes. So if we sum all these things, 16 plus 10, it gives 26. 26. Yes. So the total number of parameters are 26. If you are confused that why we are not taking the bias, because there's no sense, because if we are passing the input bias, if you must be confused that why are we are not taking the bias of input neuron. So basically, it is input layer. We just don't need bias term. Why if you build a logic, why we will be needing a neuron for these terms? Basically, why we'll be needing a bias for these terms? So basically, this is a layer which have input data points. Just their work is just for input data points. Then when we move forward, then we get the weights and bias term. Here we don't have any bias term associated or any weights coming from anywhere. No, we are giving just input data points, and then these input data points are forwarded forwarded in forward direction, or forward propagation works, and then weights are multiplied to these input data points. These input, they are just providing input data points. There is nothing like weights on the added weights which are coming. The weights are added after the input data points are weights are basically multiplied after the input data points are passed. So basically, there is no bias term associated with these neurons, basically. But after all, then after we get a bias term associated everywhere, because we get equations like for if we make an equation for particularly if we make an equation for this first neuron of hidden layers, then we will be getting a data point from this data point is coming, and then this data point is coming, and then this. So if we make if we suppose it is z1, then we can say like w1, this if we say x1, and then w2 is the weight like this, which is coming from second input data. W2 x2, if we say x2 is this. So if we say x1 x2 x3, and then we will add w3, the data from the third input uh, neuron, if we say x3. And the bias of this neuron, so basically B1, if we say. So this Z1 will be passed to an activation function, and then this will be acting as an output of this layer, which will be passed this neuron, and which will be passed to these two neurons, and then the whole process goes on. So you basically you got the understanding that how here the weights and then the biases of here, and then this the biases and weights of here is uh, basically these are the parameters which the model will learn. Input feature is not the parameter which model will learn. Input feature is the input data points which we have given. Basically w1 weights and biases are the parameters which model will learn after looking at the input data. So these are total number of 26 parameters. If we have basically this kind of model where there are three input data points, then four neurons in hidden layers and two neurons in output layers. So this is how parameter calculation is done. Input neuron is 3 and hidden neurons in 4. So for each input neuron, there will be 4 hidden neuron connected. So we will be 3 into 4, 12 weights, and then we have for 4 neurons in hidden layer, we have 4 biases. So it will give you 16, which we calculated here, and then parameters in output also. So similarly, the calculation will be done, and total parameters in the network is like this written in this. So this is how parameters are calculated, and you should know how many number of parameters, because parameters plays an important role in machine learning and in basically in deep learning. For you guys, we will be looking at number of parameter calculation using custom model, and then we will be looking at different frameworks. Basically, the number of parameters calculation using different frameworks. And I've also made written some code for forward propagation, and there is also, I think, there is also one more custom model which is used for parameter calculation. So first, we look at the number of parameters using a custom model. So here we are importing NumPy library, and then we are making a custom neural network, a custom NN class, and then we are defining different functions. So we'll be passing layers, basically layers. We have made a list basically where we'll be passing the layers. So self, then we are making a self dot parameters where this we are making dictionary in which the parameters will be stored. So making dictionary where parameters will be stored, and then we are initializing weight. So basically we are making another function of initialize weights in which the layers is basically passed. So for I in range length dot self layer, so basically if we back iterate it, so if we say there are layers 3 4 2, basically there are three input neurons. This is the same neural network structure we have, which we have basically drawn here. So you can look like 26 parameters is coming. So we are giving three input neurons, four in hidden and two in output. So basically there are the length of this list is basically uh, three. And if we pass this like length of self dot layers is basically three, and three minus 1 is equal to 2. So for the I in range, basically I will have two values. I will initialize from 0 till uh, 0, and I will also have a value I is equal to 1. So basically I can, if you remember that for range works, initializes from 0 till the value minus 1. So basically we have 2 here inside, like here the value will be 2, and then I can have values 0 and 1 if I write it in better way. So for I in range, basically 2. So this whole thing length whole dot self dot layers minus 1 is equal to 2. So for I in range 2, which means I can have two values 0 and 1. So basically self dot parameters we will be, so np random dot rand, and if we look at the documentation page of NumPy, we will look like I've already opened this in NumPy random rand. So basically we will be if we look at this 3 cross 3.2, so basically this gives us a matrix, 2D matrix. So basically, this is our matrix in which we have three rows and two columns. So this is basically used for if we look at given an array of create an array of given shape and populate it with random samples from a uniform distribution of 0 and 1. So basically, this is the thing. And in examples, we can look like three, two, basically a 2D matrix we are basically getting here. You can look at the uh, two brackets, if you know, like two is basically gives an idea that we are having a 2D matrix in which we have the three rows and two columns. So the same thing will is happening here. Like if we self dot layers I, which means that if we consider self dot layers dot I, which is given if we are taking value 0, so it will be 3. If we write the value is 3, and then we have basically I plus 1, which will give us 4. So this will give us a matrix where we have three basically rows and 4 columns. So this is the weight matrix which we are getting in this between in this thing like this is the matrix we are getting. So if you remember 3 cross 4 gives us 12. So there if you remember we have got 12 basically 12 weights. So this is represented by this thing. So we will be getting a matrix like 3 cross 4 if I so 3 into 4 gives us 12. So there will be 3 columns and 4 rows. For this, if I say this input data features, we have four neurons attached in the hidden layer. So will be like if I make some random values 12. So these are just random values like 12. Suppose the values will be very small, but we are just writing it for understanding 12, 34, 25 and 26, and then again we will be having if I look at the documentation, yeah, I am good, we are good to go. So again 6 these are just some random values. uh, So these are just random values, which basically we have made a 2D matrix in which we have 3 rows and 4 columns. So basically, is the weight matrix in between the input layer and the hidden layer. And again, if we look at this, we have a bias term, and this is when I is equal to this is when I is equal to 0. But if I is equal to If I is equal to 1, you will look like self dot layers I is equal to 1, 4, and then I plus 1 is equal to 2. So we will get matrix of shape 4, comma 2. And if we get the number of parameters like number of weights, basically, we will get it as 8. And we have done the same thing here also 4 to 8. So basically, the number of weights in between the hidden layer and output layer is 8. So we will get the value 8 here, and then again we will get a weight matrix of 4 column and 2 rows similarly like this we have done here. So basically this is the total the weight calculation. So this is basically the weight calculation, and then we have bias term. So in bias term we are only taking self dot layers I is equal to 1, I plus 1. So if I is equal to 0, then we have basically if I is equal to I plus 1, so I is equal to 0, then we have I plus 1 is equal to 1, and then we will get I plus 1 I plus 1. Then we if we look at here for I is equal to 1, we have value 4. So 4 number of biases, the same which I have told you. Like we have 4 number of biases for 4 neurons present in hidden layers. And similarly for when I is equal to 1, when I is equal to 1, we have I plus 1 equals to 2, and the I for I is equal to 2, we have 2, the value 4 number of 2 number of basically 2 number of biases. So if we add these all like 12 here, and then the weight matrix contains 12 weights, and then we have basically 8 here, and then 2 here, and then 4, then we will get. So the count parameters is just calculating all these things, and we get it returns the total number of parameters, and if we run this code, we get 26 total number of parameters. I hope you understand. Basically, here we are making a 2D matrix which contains the number of weights. Basically, the whole thing is a matrix multiplication. We'll be doing it manually. For now, you just need to understand that we get a matrix of if we have a 3 in input layer and 4 in hidden layer, so we just multiply to get 12 value, and for 4 into 2, because here we have 4 and 4 in neurons in hidden layers and 2 in output layers, and we multiply to get 8. And similarly for neurons, this has been told to you, and then just some people are looking how this thing how we have connected this to matrix thing and understand. We will do manually, and basically this is how the thing is working, and this is how by custom function we have basically calculated the total number of parameters. So I will write here for, let's just make a simple note somewhere like what needs to be told later, because I don't want to skip any part. So I will tell you manual weight multiplication and calculation. So this is basically we'll be doing later on. Looking at TensorFlow, this TensorFlow is basically a deep learning framework which we will be using, and these TensorFlow and PyTorch are already pre-installed in Google Colab. So we are using basically this. We are using Google Colab and Google Pro. The benefit of using Google Colab is that it provides some GPU computational units, so we can train our small deep learning models, and we also have an option of Kaggle, which also provides data set. So Kaggle provides some hours of GPU resources, but now we are using here. Basically, we are using Google Colab. So if we run this piece of code, so we are importing TensorFlow SDF and TensorFlow.keras.model. So basically, these are the libraries which are using. So we can look at the. I already opened the sequential model. You can run and try these codes here. It's better to read the documentation pages on your own, and this helps a lot. Like in PyTorch, also you can read the documentation pages. If you stuck, you can type anything like if in here I type sequential, so you will get what is sequential. Sequential basically is like, as the name suggests, like making a sequential model, like three input layers and four, three neurons in input layers, and basically four neurons in hidden layers, and then two neurons in output layers. So basically it's the sequence by which we are making. So the sequence here is like four neurons in hidden layers, and then two neurons in the output layers, and then we have a 1D vector of shape 3. Basically, there are three elements. We are using the same model. We are constructing the same model. So basically, this is how no, not a custom, a model is made using a TensorFlow. So basically, if we again look sequential model, if we look here, you should run these piece of code and understand. And if you stuck anywhere, you can just type in comment section, or either try in different try in GitHub, looking people, basically the GitHub of this TensorFlow, and you can also try looking in Stack Overflow, or just comment down. And if we look tens and the net is a little slow. So TFK layers dot dense. So basically, you will get to know about what is dense, and then you can also look at what are the parameters which we can pass using these functions here, like activation which we have passed here, and then the input shape which we have passed. So basically, this is how our neural network model is constructed in or defined in using TensorFlow. And similarly, you can define a model in PyTorch. So we are defining a custom torch NN. So here we are using NumPy for basically making a custom model. Here we are using basically TensorFlow for defining a model. So so you can see how tougher it was to define a model using NumPy, basically customly defining. We cannot say it's a custom model, because all these model are custom, or no model are pre-trained, but you can just so, defining like you can just not write it a custom model. You can custom model using. NumPy, and then custom model using TensorFlow and similarly PyTorch. So basically, this is how a model we made using NumPy, and this is how a model we made using TensorFlow, and this is how model we made using PyTorch. So again, we defined hidden layers and then linear because of the linear layers. And then we basically hidden layers. We have 3 x 4, 3 for input shape and 4 for hidden. And then uh, this is how basically this is how a custom model is trained, defined using PyTorch, and then we calculate that another number of trainable patterns. So if I run this code, so similarly, you can look at if we search like linear only, if we search like already we search for tens like here. So how the different arguments which have been passed and like here, we can pass units, activation, kernel regularizer, bias regularizer. These are all the arguments which have been passed. So you can try reading all these. Basically, this is about LSTM. We have come to RNN, and then convolutional 2D. This is for 2D convolutional layer which we apply, and for convolutional 3D. This is for convolutional 3D, and this is basically what everything. This is all thing about TensorFlow, and similarly for Keras also we can look, we can search here, and then we will get ping what are the different documentation pages and different uses, different libraries in PyTorch. So this was our lecture, and I'm summing up today's lecture. We have already stretched a lot, so I will be the things which we I said that I will be teaching you. I will be adding another lecture for that, and so let's end today's lecture.